Ok. Đây là ta. Chưa nghỉ hả anh Thiện? Chưa nghỉ hả? Chưa nghỉ hả?
Không có kéo. Dạ. Cắt miếng bằng keo mà không có cái kéo.
Tại để nãy không có ngoài dao bếp nó có
dao. Sao nhớ được hay ta? Sao nhớ được hay?
này phải còn bị trước á. Trong buổi này mình nói tiếng Anh hay là tiếng Việt?
Rồi mọi người sử dụng tiếng Anh. Hello.
Wow. Mọi người mọi người có một cái mọi
Just like maybe that's all. Just like I mean nothing special. Okay. Yeah. Welcome. Maybe I need to be mad. Okay, sure. Let's talk later. Okay.
You also work for Nimble?
Yeah, so I'm a designer.
You didn't come before.
Yes, because I'm pretty new and it's my first time joining the big system.
You planning to be a developer?
Yep.
You planning to be a developer?
No, because
Why did you come here?
so I'm here to see what is there in the big two step, anything that I can help or anything that I can learn to help my growth. Yeah.
What? Why does it say you with phone? The other company stopped coming.
You developer?
Yeah.
Huh? Student. You Ruby?
I have interest.
Why? Why?
I don't know. I think
For information, you want to learn something or gain knowledge are you a university student?
Which
year?
Which year? Which university?
Last year senior students.
are you foreign?
Yeah.
Where?
Kyrgyzstan. Kyrgyzstan.
The country?
Yes, the country.
Where's that?
It's in Central Asia.
Central Asia. Pakistan.
Oh, Pakistan.
Kyrgyzstan.
Pakistan. Never heard of that. How do you spell that?
K-Y-R-G-Y.
K-Y-R-G.
North of China, North of China, South Korea. There's one other country, in South of Russia, that we are what is that? Huh? What is that? The south, that is from Kazakhstan. And we are after. Usually people know what Kazakhstan is. They're large and they have a lot of oil and gas. We have, well, we have beautiful history. Good.
Sorry. What's the name? Alright. Yes. But now I want the yeah, they don't even
But do you actually go?
yeah, this is the
I went too much into the university house. Then the target lose the size of the. For example, right now I'm calling SSO, and it is very complicated because we are using the robot library. I don't know if you're aware of it, but it's supported, but it's able to configure some layers. Return, let's say, assessment and writing, it's easy to get lost.
So that means that people.
Yeah. I think one of the reasons I say that it's only yeah, that's the rest, but I'm lucky enough not to put myself in the scenario that I'm honest.
Well, we need to push encourage, remind.
The deadlines, the results. Yeah, that's a question. Yes, manage expectation and reset the expectation.
And then
Hello. Yeah, that's
So, hello everyone, welcome to the Ruby Meetup number 14. And yes, this is the first meetup of 2024. And I would like to introduce a bit about our meetup, here our Slack channel and meetup.com. I hope everyone know this meetup from this website, right? Yeah. Anyone first time here? Yeah, 1, 2, 3, nice. Thank you. Okay, and during the session, if you have any feedback, please scan this barcode. So we provide feedback to make our meetup better next time. The agenda for today, first I will welcome Fresh, and the next is about a talk from Duc, building Elasticsearch using Ruby, and after that we have break time for pizza, and finally we have a Ruby quiz from Ken. Yes. Usually after the welcome address, we have a news update about Ruby on Rails. However, for today, the talk will be a deep dive talk. It's a long talk, so we prioritize. So we will present the topic first, and the new later. So yes. So welcome our first speaker today, Duc from Nimble.
Okay, it's a bit cold here. Hi everyone. Thank you for being here today. Seeing a lot of new faces here today, so that's a good sign. And a lot of old faces as well.
not very old.
I mean, Okay, so let's jump right in. It's going to be a pretty long talk, so as usual, I'm going to speak really fast. And if along the way any of you want some clarification, feel free to stop me. Okay? Okay, so the topic today is let's try build your own Elasticsearch using Ruby. Okay, so if you don't know about Ruby or Elasticsearch, don't worry, because it only requires some rudimental knowledge about the two to understand the talk. Well, the reason for the talk is a previous month we have Zhang talking about semantic search. So why don't we try to at least understand what non-semantic search means? So have a different perspective. Okay. So the purpose, hopefully, we can achieve all of these. Hopefully, we can learn something about Elasticsearch internal. So usually, whenever you have this, whenever you see this line, it should be a sign that you shouldn't use that technology, because if you need to go under the surface to really use a technology, then it's probably a sign that the interface is not good enough. But I think the case for Elasticsearch is a bit special, because Elasticsearch by itself is very, very complex. And even though the team does a really good job of managing the interface, the abstraction still leaks out sometimes. So if you operate Elasticsearch, you might want to have some of the like internal knowledge about how it's working. And what good of knowledge if you, I'm going to put it into slideshow. And what good of knowledge if you cannot apply it? So hopefully we can come up with some useful insight about Elasticsearch. And this insight hopefully is going to guide you when you're operating and using Elasticsearch. So, and finally, have fun. Yeah. So this is a pretty fun activity for me, because to me, I mean, learning new thing about like reinvent the wheel. It sounds inefficient, but it is extremely, I think, useful to acquire new knowledge by building stuff, especially building stuff that already exists, because you have a well-scoped problem. And also, you have a working implementation that you can draw inspiration from. So, I guess. Okay. So some clarification first. Well, actually, I should name this talk "Building Lucene," because Elasticsearch actually built on top of another library. So it's called Lucene, and it's a Java library. So it's equivalent of Ruby gem. So, but Elasticsearch provide a lot of features on top of it, stuff like distributed, sharding, like, and also dashboard or API interface, like HTTP interface, so stuff like that. But we're gonna skip all that, because what we try and do today is we focus on the core technology, so the search, the query, and the indexing part. And also, I'm going to use Ruby version 3.2, not really important. Okay, so what is Elasticsearch? So this section is for those of you who never used Elasticsearch before. Well, basically, it's a database, but it's more tailored to some use case. So primarily used for searching, and you can imagine an interface. If you reduce all the extra interface, it comes down to these core functionality. So you can index a document. So index is equivalent to write API. So you write something to a database. So here you index two documents here. And later on, you're going to retrieve the data back. So we're going to call it query. So here I'm querying the database term. So if it's working correctly, you're going to get back the document that contains the database term, which is the first one here. But also you have attached to it, you have a score. So score here is 15. So I'm going to talk about the score later, but the gist of the score is it represents the relevancy between the term and the document. So you can imagine the score can be used to implement something like a Google search engine, because you have a lot of documents, but you need to rank them. So one way to do it is rank by the score. Okay, is that clear enough? All right. So if you have to draw some analogy to a traditional SQL database, then this is not a perfect analogy, but I think this is good enough. So a traditional SQL database, you have table. So table is a primary unit of data. Then the equivalent of Elasticsearch, you have index. Okay, so index is sort of like table, sort of like. And then the table is a collection of rows. And then you have document. So index is a collection of documents. So if you use a database like MongoDB before, you might be familiar with the term document. And then a row, which will subsequently be made of columns. So there's multiple columns, and then document also made up of multiple fields. And there's actually a hidden level here. I'm gonna get to it later. Okay, and Elasticsearch is very complex with many features. So we're gonna scope down it a bit. We're gonna focus on the index, so the write API, the query, the read API, and also the filter. I'm gonna go to detail later. Okay, so let's try index. Okay, so the unit of indexing is document. So in here, you're indexing a document with two fields, text and title. So text is Postgres is the database, and title is Postgres. So for simplicity, we're gonna allow user to search only on the text field. So to simplify the problem. All right, here's the plan. First, you need to give back the user the document, the original one. So obviously, you need to store it somewhere, somehow. So that would be, the purpose of the document storage. So this component will be the one storing your document, and then later on spits it back to you. So this is the one, and the high-level plan is let's say you have two documents here, and you're going to index it into a database, and later on you're going to query it back. Let's say we query it with the term database, and you need a way to identify the document. So let's use a simple auto-incrementing integer here. So I'm going to assign this document to ID 0, this document to ID 1, okay? And then when I'm querying, what I'm going to get back is the list of documents. So because the term database here is presented in both of documents, so we're going to return 0 and 1. And finally, we're going to pass it to document storage, said, hey, give me these two documents. I want these two. And that's the high-level plan. So there's any conclusion about this? Okay, so I'm going to move on. Okay, so we're going to try to implement each component individually. So it's good to have, I'm sorry.
So you mentioned that index is kind of like a table.
Yeah.
But in this diagram, it doesn't seem like it's a table.
Can you elaborate a bit more?
Like in previous slide, you said that index is kind of like an SQL table.
Yeah.
Right? But in this diagram, it doesn't look like a table. It looks like some kind of action.
Yeah, just because the way I draw is I want to represent the data flow. So how we're going to interact with the database and how the data is going to flow. But if you look at it like from the outsider's perspective, it acts like database because you have document as a row to interact with. You can update it, delete it, insert it, and you retrieve it back, and you can identify it with some sort of number. So the underlying representation is obviously important, but the interface is very much similar.
No, but in this diagram, index, does it mean more or less a table, or it means some kind of action?
Oh, yeah, I'm sorry. Yeah, it's very confusing. Yeah, index is also a verb and also a table. So yeah, Elasticsearch makes it kind of confusing that way. So you index a document into an index. Okay, does that make sense? Okay.
And document storage, I suppose, is sort of similar to active record collection?
You can think of it that way, but you can implement it in many different ways. But we're going to try a different iteration of it. But okay, so the first component is document storage. Okay, so let's step back and try to think about the high-level interface. So the high-level interface is going to be as simple as you have something to write to it, so add document, and then you have something to read from it, get document, and that's it. And we're going to try to fill in the blank. Okay, so let's think about the layout on disk, because obviously you need to store the data on disk because you need to persist it and retrieve it back somehow, so it needs to stay on disk. So therefore it needs some planning about layout. So a simplest layout that I can think of is you laying document, this is a file, and you try to lay document one after another consecutively, like laying brick. So one after another and another. So I have document 0 here, and then 1 here, 2 here, and if you zoom in a little bit, you're going to see the structure of an item. The reason we have to store the length because unlike the bricks, different documents have different length of the payload. So this document is going to be big, another one is going to be small. So to be able to correctly retrieve it, you need to store the information about how long it is. So I'm gonna get to it later. And again, the payload needs to be serialized somehow. So let's pick JSON because again, it's simple. So we have length and then payload. Usually we refer to it as length prefix. So you prefix some payload with a length so you can later retrieve it back. So, all right. So looking at this layout, here's how you encode it. So first, you grab the payload, you JSON stringify it, and then you prefix the length. So here's the file. You're gonna say, hey, I want to encode the length as a binary string. This flag here means I want it to be 8 bytes. All right, and then I'm gonna store the payload, and then I'm gonna flush it. So directly translate it from this diagram. And the decode part is just the inverse of this. So actually this is completely generated by Copilot. So it's very cool that they can do that. I didn't have to modify a single character for it, even though this is completely made up nonsense by me. And the way you do it is you read the payload length. Okay, you're gonna say I want to read 8 bytes because that's how long it is, and you're gonna unpack it. So like convert it back. I want the length, and then I want to read that amount of length. So I want the length. I want to read that amount of length, and then I parse it back. Okay, does that make sense? Want to ask something?
Yeah, but in the real scenario, the 8 numbers gonna be dynamic, as you said, every way.
Yeah. Well, actually, the 8 number is not dynamic because the 8 number is gonna be 8 is gonna be the number of bytes you store the length. So I'm using 8 bytes because I'm not sure how big the length is, so I'm choose the biggest number possible. So yeah, so we use 8 bytes to store the length. So it's possible for a document to exceed that length, but it's very unlikely. It's few gigabytes. I'm sorry?
8 bytes is 64,000.
Nah, it's bigger than that. 8 bytes you can use to address the memory. So with 8 bytes, I think you have something like 200 and something gig. I'm not sure though, but I'm pretty sure it's enough. Well, you can always bump this number up. Yeah, it's huge, but you'll always bump this number up.
With near not bigger than that.
Yeah, true. Actually, Elasticsearch has some cap on it as well. I think you cannot index something more than 100 megabytes. I'm not sure about the number, but there's a cap. Okay. But the problem with this scheme is there's no random access. If I ask you, give me document 2, there's no way you can quickly retrieve it. The only way you can do it is you walk the whole file and then you count until you reach the document that you want. So we call this sequential access. So sequential access is not bad all the time, but particularly in this case, when you want to retrieve discrete elements, so I want to say get 2, I don't want the rest, or I want to get 10. So we need to provide some sort of random access to this structure. Okay, so we're gonna implement an index for this file. So this is, I know this is index is a very familiar term with you guys because probably you guys have heard it using database like Postgres, for example. So a good analogy that I can think of is an index is like a table of content of a book. If a file is a book, then the index is the table of content, because the table of content provides you random access to the book. For example, if you want to look for, let's say, chapter 12 in a book, without the table of content, you have to skim every page of the book. You have to flip through the book, and hey, I found chapter 12, but that's obviously inefficient. And with table of content, you can do some sort of thing like you first consult the table of content first, and you find the chapter. You say, hey, it's the page number. The page number is here, and you can go back and then immediately access. So that's called random access. I'm sorry?
You need to make sure that you open the right page, right? So you still do file research.
Yeah, but that would
It's not random.
be, yeah, that's a good point. That's not like, but in this, if you know the page number, you can, but in
It's still on the disk, it's still local. Still file research in RAM if you want to have flash memory.
Yeah, I think you got a point. Okay, so the index is equivalent. Again, its structure is very simple. You're gonna store the offset into the file. So the equivalent of the page number is the offset. So if you look back at this diagram, what do I need to find this to this document? What I need is offset to the beginning of the file. For example, this document, its offset is 0, meaning it starts at the very beginning of the file. And this document 1, its offset is going to be something, let's say 24. And doc 2, its offset is going to be, let's say something 36. If you somehow manage to get that offset, you can quickly retrieve back the document. So that's exactly what we're going to store. So we're going to store a pair of document ID and then offset. Okay, doc ID and then offset here. So 0, 1, 2, and here's the offset. So this is the page number that we're talking about. All right? Is everything not clear?
Yes.
I'm sorry. Yeah.
So could you please elaborate like how does the offset? For example, in the middle row 1 and 48.
Yeah.
So the 48 offsets mean I can get to the mid row like 48 plus from the previous one.
Yeah, you kind of get it. Okay, so let's say you want to retrieve the first document.
First.
Okay, so the
Example,
one. I mean, I'm sorry, the one. Yeah,
The
it's very
one
confusing.
that-
Think of this as an array, right?
Mm.
So 48 is the first element of your new document. And everything is an array, right? It's much easier for us to start arrays than right? So 0 is start at 0, 48 is the documents are at 48, and 102 starts at 102. And that's what we so I'm going to 102, and you start with 8 bytes to know how much you need to do the next one.
So the short answer is yes, right? So I can get to the middle one
By reading
by reading 48.
48 plus, so you start at 48 and read 8 more
Okay.
to have the paper.
Okay.
Yeah, I'm gonna show you the code later, but yeah, Octavian got a point. Yeah, he's absolutely on point about it.
Okay. Thank you.
Okay, so we need to store it. We need to store an extra thing in the index. So we got to store the document first, like we did before, and also we need to store the index. So to this diagram, you have document ID and then offset. So we have document ID here, and then the offset here, and you're going to store it, and you're going to pack it, and again, and also you're going to need to keep track of the offset. So every time you index something, you need to bump this number up.
Why do we need document ID and offset?
That's exactly the point.
You need to store two things. You need the tables for the table of contents, you need the table of contents, and then you need the book, the actual book. So those are stored in different places. You first store the table of content. To build table of content, you need to know when you start, how much you store before. What's the next step?
Octavian is right, but Mark is also right. So my very first implementation, I didn't have to store doc ID because we're storing everything sequentially. So it's basically 0, 1, 2, 3, 4, 5, 6, and you can omit that part. But the reason that I added back is later on you can have gap in between because you're gonna support delete in between and stuff like that.
Support what?
Deletion. So it's gonna be have gap in between. So your scheme is no longer work anymore. If what I'm understand you're trying to say is if you don't have document ID, you can take the numbers.
Yeah, because like if the analogy is with an array, it's enough to know
It's not
index.
array, it's like a string text base. You say the old.
I mean, the document ID is what you actually want to search, like a table of contents, chapter 10. That's the document ID, right?
Yes.
It's not just 1, 2, 3, just what you want to search.
Okay. But yeah, good point by both of you. I'm gonna move on. Okay. And again, you're right. We're gonna do a binary search because let's say we want to get a document, the document ID. Let's say this one. Let's say we want to get a document ID 2. Well, so basically it is a sorted array, increasing order of the document ID. So if you want to wrap something, just a simple binary search would do. But the only difference is the array is gonna live on disk now, not on memory as you usually deal with.
It's much shorter, right?
I'm sorry?
The stuff you need to read is much shorter.
Yeah, that's true. Okay. Okay, so once you get the binary search and you get offset back, and to answer the question of Tien, let's say we get the offset back 48. So there's an API to skip the cursor to this position of the file and say, and you tell, hey, I want to read some data from this file, but starting from this cursor, from this offset. So it's equivalent to turn the page and stop at that page of the book. Does that make sense? Okay, so that's how the offset is going to work. All right. So that's pretty much it. So that's very much it for the document storage. You got only 2 API. I'm done with it. Okay, I'm waiting. way out of time. Let's try to go even faster. Okay, so the second component is the term dictionary. So if you look back at our original use case, there's a core question that you need to answer. The question is, if you give me a term, can I give you back the list of documents that contain that term? So the question is, so the core question is, what is the mapping between term and then the list of documents contain that term? And Elasticsearch refers to such list as a posting list, so I'm going to use this term from now on. And the structure is referred as an inverted index in the documentation. So why inverted? Well, a forward index will map a document to the terms that it contains. So a forward index will answer a question, which term does this document contain? And the invert one answers the opposite question. So the invert one is going to answer the question, which document contains this term? Okay, so
Term is just a word.
oh shit, I forgot to include that slide. Okay, I'm going to go through it right now.
Yeah, tell me just the word.
You got a point. Term is not always the word. Okay, you're sharp today. You're asking a good question. Okay, I'm going to go to later. Well, if you look at these two documents, I say you have document 0 and 1. So this is basically how it will look like. For example, Postgres, you have a posting list of 0 because it's only present in this one. And database is going to be 0 and 1 because it's presented in both of the document. And the rest is self-explanatory. Okay? So to answer Mark's question, we need to discuss the definition of terms first. So what is terms? We use a component tokenizer to break down the field value into terms. So you have, let's say you have a string, and you feed it into a component, let's call it tokenizer, and it will spit out a backup terms. So what is the definition of terms? Well, actually, you can tailor the definition to a use case. So for example, we have an email here. You can say, hey, I want this whole email to be one term only. Or you can say, hey, I want this one to be a term and this one to be a term. So 2 term, or you can say, hey, I want all 3 of them to be a term. So different use case, you can tailor the tokenizer to a use case. For example, if you only want your user to be able to search email if they type in completely full email, you can pick the first one. And if you want to support partial search, you can search without the domain, you can pick the other one. Does this answer this question, Mark?
Yeah, and I suppose in your implementation,
Yeah.
term is just separated by spaces,
Yeah.
right?
So, okay, you're like a prophet. Okay, in my implementation, it's only it's actually an alphanumeric only, and I cap the length to 255. Usually the term shouldn't go longer than this, and we normalize it by downcasing it. Okay. But you can completely write a customized tokenizer for Elasticsearch. They allow you to do that. It's very useful as well. Okay, so the tokenizer is just simple as this. You feed into text and you spit out a list of terms. And well, here's the term dictionary interface. Okay, so the simplest implementation that we can think of is basically a hash map. So we're mapping between term and then posting list. So here, dictionary is a hash map. If we add term to it, we're gonna go through each term and then shove the document ID to the array. And then if you want to retrieve it back, it's just basically a hash map lookup. So it's just as simple as a hash map. And also you need to store the term dictionary on disk somehow. So you need to persist it. And again, we have to visit the file layout on disk. Well, the file layout is going to be much more simple. And we're going to store, again, pairs of term and then posting list. And each one of them have prefix length as well, like I mentioned before. So here's the implementation. Sorry? Yeah. This is basically my payload. Okay? And the only difference is for the term, I only need 1 byte for the length, because as you see, I capped the term at 255 character, so I only need 1 byte to store the length. That's why you need a different flag here. So C flag, and then you said, hey, shove it to the 5, and then again, you prefix the length. So the length is going to be the amount of document here. So here's 3 document. The amount is 3 times 8 is 24. And again, that's it. And you flush it. So you basically persist the term dictionary on disk. Well, there's only a catch, is that persisting is a very expensive operation. You do a lot of disk write and you're iterating through the whole dictionary. So for the first version, to be able to complete the benchmark, I have to do it every 3 seconds, because there's no way my MacBook going to survive that. So I cheated a bit. It means that you're going to lose data during that 3 seconds, but let's just ignore it for a while. Okay, so at the same as sanity check, you should revisit the query path a bit. So now, user going to give us a term. We're going to push it to the term dictionary. The term dictionary is going to spit back a posting list, which is a list of documents that match it, that contains it. And then we're going to take that posting list and feed it to the document storage. And finally, you're going to get the original list of document back. Okay, benchmark version 1. Okay, so the benchmark suite I use it. I try index 900 megabyte of Wikipedia article, so close to 27,000 articles something. And the speed is, not good. The problem is we use so freaking lot of memory. So this 4 gig for a few documents, because we're holding everything in memory. As you can see, we're holding the whole term dictionary in memory. So the memory size is freaking wild. And also, you see here, the performance decrease over time, because as the term dictionary gets bigger and bigger over time, the persisting takes longer. And in the end, I couldn't index any document because the persisting takes out everything, takes up a lot of resources. Okay, does it make sense? Okay, let's try and improve it. Version 2, okay. Well, the term dictionary is too big. That's obviously the problem. And eats up a lot of memory, and persisting takes so long. We could try to improve it. How about we split it? So we're gonna split into 2. So we're gonna store the posting list, which is the array, in a different file. So we'll call it a posting list storage. And then in the term dictionary, instead of storing the whole list like before, again we're gonna use the same trick. We're gonna store the offset only. Okay, again. So the offset is like a pointer to a book that you can retrieve the content later. So we're gonna split into 2. Postgres now will store 0 only as the offset, and then this one is going to be stored on disk. Well, the rationale here is instead of storing the whole array, you're now storing 1 number. So it gotta be better. It gotta be better. Hopefully it will be better. I'm sorry?
I don't see why, because you're still writing both of them.
Yeah, but the memory should help. It should help with the memory. Because
The RAM memory or
yeah, the in memory, the RAM memory. Do you want to ask something here? It feels like you try to ask something. Okay, benchmark. I was wrong. Well, kinda. I was kinda wrong. Okay, I was really disappointed about myself. So the indexing speed does increase, but by a tiny bit. And we didn't solve We didn't solve the problem of performance decreasing over time because it's still there. It's still the same shit. But the peak memory does reduce by a bit. But by my calculation, this is way off. By my calculation, we should save something close to 25%. But this is nowhere close to 25%. So this is obviously some bug, but I haven't found yet. But the bottom line is we save some memory. So that's good. That's not good enough. Okay, so let's take a step back. What is the fundamental design flaw that we have? It's obviously something that we do seriously wrong that hinders our ability to improve it. And we're rewriting a lot of data. And rewriting data means unnecessary work. So for example, for the whole 3 seconds, you did not index everything, you did not index anything. You still have to take the term dictionary and persist it, even though there's absolutely nothing changed. So, and also, if you index only one document, you're still rewriting the whole thing. So that's the flaw of the design. So unnecessary work, and also, so persisting term dictionary is very wasteful. And also, update posting list is also wasteful. If I need to add another item here, how can I do it? I can append it to the bag, an array, but the result is I'm going to show off everything in the bag by some offset. And it means that I'm going to rewrite the whole thing. So if I need to add something here, these guys are going to have to be pushed back by a bit. So the way to do it is I'm going to take it out, add a new document, and then persist it back or append it back like a new one, and then just forget about this one. So ignore its existence. So, but obviously, if your posting list is really big, you still end up rewriting a lot of data. For common term in English, for example, and, the, and, or, so those are very common terms. This list is going to be freaking big. Rewrite it a lot of time. Okay? Okay, so I'm out of idea at this point. So I'm turning to Elasticsearch. How Elasticsearch does it? Well, Elasticsearch asks a real weird question. What if every time we index a document, we write it to a new file? Instead of touching the old file, it tries to write to a new file? How's that going to help? So with that structure, the index, so the table that you mentioned, is actually made up of a lot of mini index. We call it mini index. So it's like a mini table that lives inside a table. So the good analogy is a shard, a database shard. It looks very much like a table, but actually together they made up a bigger index. Okay, so I'm gonna explain what segment is. So every time you push some data to the index, you don't touch the old file. You create a new one. So we have segment 0, 1, 2, 3, and 4 here. So like different file all the time. Okay, I know this is very unintuitive, but try push through this. But it makes a very interesting characteristic, is that segments are immutable, because every time you're going to write something new, you're going to append to a new one. So it means that the old one, the old segment, is going to be freeze in time. No one's going to touch it. So there's no modification will be made to it ever again. So these black segments going to be unactive, so they are mutable. And there's at any given time there's only one segment that was active, which is the green one here. So remember this, because this is going to open up a lot of different doors, different optimization that we can have with this characteristic. Okay, everything is exactly the same as before, but the only difference is I have to append a folder to a data path. So normally this guy will live inside data, but now it's have lives inside another folder, and that folder will be the segment we're talking about. So everything lives inside subfolder. So this is a segment, this is a segment, and as you can see, the structure of the segment is exactly identical to an index. It's functioning exactly as an index. It's got every component that we just mentioned so far. That's why I call it a mini index. That's the reason. But we have a problem. We create way too many segments. If you create a segment for every new index, for every new document, we're going to quickly run out of inode limit on the system. So basically, you create way too many files. The operating system cannot keep up with you anymore. And also, query will take longer. Why? Because now you have many small things. You need to visit all this to be able to look up anything. So query will be slower, and then there's a limit on how many files you can create as well. So that's a problem. So the solution is you run a background thread to merge the segment. So there'll be two guys. One guy keep creating segment. Hey, I'm creating new one for every index operation. And then the other guy coming from the back. Hey, I'm gonna clean up for these guys because there's so many segments lying around. So, for example, if you have 3 segments here, I'm gonna grab the 2, merge it into the third one, and then delete the 2. That's how we're gonna try to contain the number of segments. The implementation is really long, so I'm gonna spare you that. But basically, we need to merge each component. So for the document storage, it's just simple as concatenate, because it's just a book. So you concatenate 2 books into one longer book. That's it. And for the storage index, you need to merge it, but also you need to maintain a sorted order, because if you remember, okay, that's really okay. So you need to keep the sorted order here because you want to do binary search on it. So remember, merge 2 things, but keep the sorted order. It's a simple problem of merging 2 sorted arrays. So I'm pretty sure you're all familiar with it. Okay. And term dictionary is you merge them and then also combine the posting list of the same term. So if you have Postgres, Elasticsearch here, and then Postgres database here, what you want is the final result. Postgres is going to have the posting list from both segments, and then merge everything into one. Okay, I'm going to leave here for a few seconds. Okay, is that clear enough? Okay, so the merge is really...
I don't understand the document storage index. Because if you concatenate the document storage, right, you get 1 and 2, then the index should be plus what you have in the first one, right? Right, the page in the second one, when you measure document storage index, the offset of the second, the first one will be whatever you have in the first one plus the offset.
Yeah, exactly. So the offset is only simple that you bumping the second one by the size of the first one.
Yes, exactly.
But the document ID need to be maintained sorted.
But the document ID is the document. Are they different, right?
They're different, yeah. So it's a chapter number. You need to keep the chapter number sorted. Yeah.
This short we call binary search or any other purpose.
Yeah, it's sorted because we need to perform binary search on top of it. And also, if it's sorted, there's, again, some optimization that we can do later on, but primarily we need sorted because we must do binary search. Okay, so here's the insight for you. Hopefully you can search something for this. On merges, this is actual Elasticsearch. Merges a very expensive operation. So if you're operating Elasticsearch, should pay attention to this. If you have unpredicted performance, this might be the cause. Because imagine if you merge two gigantic documents, or two gigantic segments, you can end up rewriting the whole thing into a new one. It's like having two giant bottles of water and then take it out, pour it into a new one. So you're gonna read a lot of data from this, you're gonna write a lot of data, you're gonna need a lot of memory, a lot of object allocation, causing a lot of GC pressure, all that stuff. So, and this event only happens once in a while. So it's not easy to catch it during this action. So you might want to pay attention to it. Okay, so here's version 3. Okay, I was wrong again. How the frick? Okay, the indexing speed is significantly slower. It falls down to 1.2. The peak memory does reduce by a lot, so it's a good sign. But the disk size, so the total disk that I consume went up by.
Keep the whole data, right? So of course increase the
Yeah, yeah. But
if you write more, you need to write more, so of course the speed decreases.
the speed increase. No, the speed does not increase. Decrease. Yeah, because
You need
yes,
to write more from
you're right.
You do the merge extra.
Essentially you're doing double the work. You pour the water into two different bottles and then just to put it back into another one, to third one. So you're doing a lot of water pouring. And the disk size could be explained by the amount of files we create. Each one of them has a certain amount of overhead, so together they cause a big bump in disk size as well. Okay, I promise this is gonna be the last one. I'm freaking bored with it. So this is gonna be the last one. Okay, the problem is we still create way too many segments, even though like we merge it in the background, and the background merge cannot keep up with it. And there's no way the background merge can keep up because it's an inherently more expensive operation. So the 1:1 ratio between documents and segments is too small. You need to bump it up somehow. Okay, so solution is as easy as buffering. So instead of writing every time you receive a document, you shove it into an array. And then once it exceeds the size, I set the size here to be 256. So once it exceeds a certain size, we're going to do a flush all of them together. Okay. It's just simple as this. And again, buffering is not a free meal, of course. Buffering is fundamentally a trade-off between latency and throughput. So latency means that now there would be a latency between the time that you write the data and the time that you can actually query the data. So there's a time in between that your data living inside a buffer. So there's a latency in that. Some system cannot tolerate it. Some system can. So you might want to configure the buffer size to match your applicant use case. So you might want to tweak it to match the use case. For example, at our previous company, we use Elasticsearch to build a filter system. So for example, a customer can change an order status to delivering into completed. And then immediately after, they filter the complete order. So certain customer complain that, hey, I just do it, but where's the freaking filter result? It should be on top. But there's nowhere to be found. So a few seconds later or a few minutes later, depends on the use case, it appears. So you might want to twist this number. Okay, so the benchmark. Okay, finally, a decent version. Well, actually, we climb back to the indexing speed of the original version. The peak memory does increase a bit. Well, I think you can explain it because we're essentially buffering data in memory, so it got increased by a bit. But I think 80 megabytes is still too big, so probably something else. So I'm gonna investigate it later. And also this says, I'm sorry?
The terms.
The term? It could be, but 256.
You have a lot more.
Oh yeah, you're right. Because each segment is bigger, so you need bigger room to store it and to do the merge. So you need a bigger area to do the merge. Yeah, it could be. Yeah, very good point. And the disk size is decreased a bit because we create a lot less file. And here's a final bit, delete and update. So if segments are immutable, how can we delete documents? Because like I said, you're not allowed to touch the old one. You're just allowed to write a new one. So how do you delete? Well, we cheat a bit. We set a flag in the document. We set a flag and tell that, hey, this document is dead. If you see it during the query, it means this document is gone. So just keep it. So this technique is used in a lot of databases. It's called Tombstone in Cassandra. In Postgres, we call it dead tuple. So it's very common technique. And also, we're going to remove it during the merge. So when you're doing the merge, if you find someone who's already deleted, just toss it out. And that's it. So which means that after you delete some documents, it will take you some time to reclaim the disk space. It happened to me once. I delete like half of the index to save disk space because the node is running out of disk. I panic, delete half of it, and nothing changed. The disk size actually increased because we need to set the flag. So what the fuck just happened? And then I think a few minutes later, it went down. So this might be useful if you found yourself in a similar situation. And then update is just deletion plus insertion. So basically two operations. You delete that and you immediately insert a new version of it. So the update version. So
Deletion is also insertion.
Kinda, yeah. Kinda, yeah. But it's more like you tweak the flag just to say that hey, it's dead. And
But to tweak the flag, you need to insert it again and then you look.
Usually you're gonna spare 1 bit for it at the entry. So you're gonna spare 1 bit for the flag, and then you're gonna flip the bit. That's it. So you don't have to append or anything.
But you still need to write the whole document again, read and write again.
Yeah.
The whole segment again.
Not sure if the whole segment. There's some implementation that they store the flag separately. So there's that. So if you store the flag inline,
So
yeah.
you have another deleted tables.
Yeah.
And then you.
Yeah, that's the point. But it depends on the implementation. Okay, so update is deletion plus insertion. So update is inherently much more expensive. So if you can avoid it, please avoid it. Okay, finally, after all this, the rest should be smooth sailing because we got a structure by now. So query is very simple. You need to pull data from all the segments, and that's it. You're gonna list all the segments, flat map through it, and then you query each one of them. And with each one of them, you just perform the intended routine. You get it. You get the posting list from the term dictionary, and then you map through it and you fit it into the document storage. So basically, the idea is that the sub problem is querying from one single segment, and with this, there's a chance to optimize it. This is an embarrassingly parallel problem. It's very, very easy to parallel because segments are inherently isolated from each other. They share nothing. They exist as like a separate index. So there's an optimization chance that you can parallel the. Also, there's no lock involved because once the segment is there, there's nobody's gonna update it. So usually in a traditional database, when you try to read something, you need some mechanism to make sure that nobody else write from it. So this a naive implementation would need to do that, but you sidestep the problem here because it's immutable. No one's gonna update it while you're reading it, so no lock involved. Okay. Well, so another aspect of querying is scoring. So once you have the list of documents that match your query, you need some mechanism to rank them. So it's like Google search. Once you have the first page, a list of 20 entries or so, you need a way to rank them. Okay, so how we're going to do it? So scoring is answering the question, how relevant is a document to a query? So how relevant it is. So let's reduce it to one simple example. For example, if you want to query, let's say, I know I didn't implement the OR conjunction yet, but it's really easy to implement. So let's just pretend that we have that. So we're going to query duck or goose. So everything that contains ducks or goose is going to be considered a match. We have three candidates here. One duck, another duck, one duck, another duck, and another duck, and then my name is Goose. If you look at these two, if you isolate the duck, so there's three documents that match the term duck. Can you guess which one is more relevant? The second mean. Oh, okay. Yeah. Why? Like, do you have any reason for it?
Number of repetitions.
Yeah, you're right. So the intuition is, the rationale is, the documents which contain more terms are generally more relevant. So if you guys have done SEL before, like search engine optimization for Google, this is very textbook. So it's one way. So it's a signal that say, hey, the second document contains three times the term duck. So probably more relevant. So the concrete implementation, so I just took it from the Elasticsearch documentation, is the square root of the term frequency. So you don't have to care about why the square root here. The bottom line is, if term frequency goes up, the score goes up as well. So more term mean better score. Okay. So if you isolate the 0 and the 3, oh, this is really confusing. 0 and 3 document, can you guess which one is more relevant? Sam?
Number 3.
That's the first one.
First one?
The 0, 1.
Oh.
Because,
0, 1, yeah.
For the OR condition, if the first one is correct, then we need to care about the later. That's my assumption.
Yeah, also a good point. What about you, Tavian?
I think Goose is longer.
Goose is longer. Okay. That's actually a pretty good point. I didn't consider it. Okay. Your answer is correct, but just by chances. So the rationale is the common terms are less important than uncommon one. So here, goose is uncommon term because it's only presented in one document, whereas duck is much more prevalent. It appears in 75% of the population. So, if I have to consider, probably the uncommon one is going to win. So the implementation is, again, it's very long. It's total document. So total document here is 4. So the total amount of document that you have, and then you divide it by the dot frequency, which is how many dots contain a term. So the bottom line is, if the dot frequency goes up, the score goes down. So More document has the term, the worse the score. Okay? And you repeat that with every term in your query. And then you sum them up. That's it. This algorithm is called TF-IDF. So it's very like hideous name, I know. TF is term frequency, and then IDF is inverse document frequency. Okay, very mouthful. And that's pretty much it for scoring. But Elasticsearch actually have a few more components. And if I remember correctly, they have something like 6 or 7 different components, adjusting for different like scenario to try to not overweight. Okay, finally, you have the filter. Well, filter means along with the query, you can specify some condition as well. So it's like the where of a traditional database. So you can where that a category must be programming. So hey, I want to search for Ruby, but only in category programming. So you're gonna consider these 2 terms only. So that's the filter. And behind the scene, the filter is implemented exactly the same as we used to, but we just skip the tokenizing part. So user gives anything, we just keep it as is and index that. So no breaking down. And yeah, so here's what it looks like. So programming is going to present it 0 and 1, and material is going to present it 2. So this one. So this is very similar to the traditional indexing we just mentioned. So what makes filter different than normal query? So this is a good question to ask. The filter doesn't care about scoring. It only answers yes or no. So that's a fundamental difference. So the filter gives you a binary answer. A document either passed the filter or didn't pass the filter. So there's no scoring involved. And it means that the result of filter is static. It's not affected by other documents. If you remember about the scoring part, the result of the scoring is actually dependent on the outside environment. So the more document you add to your index, it's going to affect the score. So it's not static, it's dynamic, but filter is different. It doesn't care about the score. So the result is static. So static means catchable. So we should catch it. So how do we represent the filter catch? As bit set. That's the most compact way to do it. So if you have 3 documents here, and you try to catch the filter, hey, I want to filter everything with category programming. And the representation is going to be a bit set. So it's going to be a length of 3 bit set, 1, 1, 0. 1 means match or satisfy the condition, and 0 means does not satisfy. And the bit set is very compact. If you think about it, if you need to store a cache of 10 million entries, you only need 1 megabyte to do it. 10 million entries, 1 megabyte. So it's very compact, it's very efficient, and if you do compression on it, it's even gets smaller. And cache are tagged to segment. So as I said, different segments exist isolated from each other, so they're gonna have their own cache. So the segment here is gonna have these 3 the cache here, and the segment 1 gonna cache here, and also the cache need going to be tied to a particular value. So here the cache is going to be tied to the value of programming, and also the cache is going to be tied to the value of material. Okay, here's the cool part. Segments are immutable, so there's no cache invalidation involved. Again, because of the characteristic of a segment is immutable. So as you already heard before, the 2 hardest problem in programming is cache invalidation and naming things. and we just sidestep one of them. So there's no catch invalidation involved. And we could easily combine different catch. You could combine multiple catches in a single query. So for example, if you add two conditions, right, category programming and then subcategory framework, and they have these catch, it's just a simple bitwise AND together because the segment length is the same, so the length of the two masks is the same. You just stack them on top of another and then have the result. This is extremely efficient. You can do several bitwise operations like really fast. This is one of the reasons I really like Elasticsearch is Elasticsearch make use of multiple index really well. So traditional database, in my experience, usually suffer if you specify multiple filtering and query condition together. So they're not very good at combining different indexes. So if you have an index for A, B, and C, and you try to query across all of them, usually they just pick one. Just pick the most sensible one, do the work, and then do the bare hand filter to the rest. But Elasticsearch is very efficient. They can utilize all the index that they have with a very special. But again, there's no free meal. Filter caches consume a lot of memory. So this is probably the biggest source of memory consumption. Not biggest, but it's very huge. Depends on the use case. Also, slow cache warming up means performance are worse during startup. So Elasticsearch, if the cache is already warm, so usually you have pretty good performance. But if you just booted the code, you just booted the instance, usually it needs some time to warm up the cache. So the performance at the beginning is going to be not as expected. So you might want to have some extra care around that. So there's a lot of ways to deal with this. Okay, so there's another section compared to Elasticsearch, but this is just something that we can improve on our existing design. But I think this talk is already long enough, so if you have any question about that section, you can ask me later during pizza. Okay. And the implementation is living here in this repo, so if any of you interested, you can see the actual implementation here. Yeah, I'm gonna leave it here in case anyone interested. Okay, that's it from me. Thank you for being here.
Okay, so now we enjoy pizza.
Okay, gather everyone, we have pizza.